I'm going to show you a beautiful proof of this elementary set theory theorem using prime numbers. And I'll firstly review what it is, and it's going to be a super cool proof that they don't show you in textbooks. So here we have the statement that a finite product of countable sets is countable. So a quick review of countability, which will be essential in our proof as well, is that a set is countable. So we say that a set A is countable if you can enumerate the elements of A, which is to say that if there exists a bijective function from the natural numbers to A, okay, from f from n to A, where n is a set of natural numbers, so n is going to be essentially 1, 2, 3, etc. And to say that there is a bijective function from n to A means that if you think of the an as being equal to the image of n under f, you're basically saying you can enumerate all the elements of A as a sequence an, where if n not equal to n prime, an is not equal to a sub n prime, and all the terms in A are going to be some term in the sequence. Okay, so you can enumerate in that way. Then we say f is bijective and A is countable. Okay, so we want to prove that a finite product of countable sets is countable, and the prototypical example, because essentially once you know a set is countable, you know it can be enumerated by the natural numbers. So what we really want to prove is that the set nk, the Cartesian product of n with itself k times, n cross n dot 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 k times, that this set is countable, that we can enumerate all the elements in this set. Okay, and the enumeration is going to be using prime numbers. So how is that going to work? What I'm going to do is I'm going to define a function from nk to n that is 1 to 1. And then I'm going to explain what the enumeration is, and the function is going to be defined using prime numbers. Let me erase this part of the board and do so. We're going to define the following function. So we fix k, okay, we're looking at the Cartesian product of n with itself k times. So we fix k, and let's write p1, p2 up to pk to be the first k prime numbers. Okay, the very first k prime numbers. We know there are infinitely many, so no matter what k you choose, there are at least that many prime numbers. And now we're going to define a map phi from nk, the Cartesian product of n with itself k times, to the natural numbers, and the map is going to be defined as phi of a1, a2 dot 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 up to ak. So a k tuple of natural numbers is going to get mapped to p1 power a1 times p2 power a2 dot 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 times pk power ak. Okay, this is going to be our map. And the first statement I'm going to make is this map is actually 1 to 1. Okay, it's a 1 to 1 map, which we denote by that symbol there. In other words, if you have distinct k tuples in nk, their images are going to be distinct natural numbers. And that's so beautiful. Okay, so in other words, we want to prove the contrapositive. We want to show that if we can say that p1 power a1 dot 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 pk power ak, if that's equal to p1 power b1 dot 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 pk power bk, so another k tuple b1 through bk is getting mapped to the same thing, then the k tuple b1 through bk is also equal to the k tuple a1 through ak. Well, why is that? If you have an equality here, because all the ai's and bi's are going to be natural numbers, the fundamental theorem of arithmetic that numbers factor uniquely into products of powers of prime numbers implies that by the fundamental theorem of arithmetic that ai must be equal to bi for all I, and that shows that the original tuples are equal. So this is going to be a 1 to 1 function from nk to n, and so that means that, you know, whatever the image of the function is, okay, it's not necessarily on 2, because of course there are going to be natural numbers that aren't divisible by any of the first k primes, so it's not going to be on 2, but whatever its image is, it's going to be something that we can enumerate. Because essentially we do the following trick. We can say that, okay, let's look at the smallest natural number that's in the image of phi. Okay, we can call that x1. Okay, so let x1 be the minimum element in the image of phi. And then what you can do, I'm writing it out in this notation, and then you can define x2 to equal to the minimum element in the image of phi minus x1. Okay, minus just x1. And then you can keep on going. In general, you can inductively define xn plus 1 to be the minimum element of in the image of phi minus the first n elements in the image of phi, x1 through xn. And now the cool thing is that this defines an enumeration of the image of phi, and it's going to exhaust everything in the image of phi. So therefore we've shown that the image of phi is countable, and of course nk to the image of phi is a bijective function. Okay, so therefore if we can enumerate the image of phi, we can enumerate nk. That shows nk is countable, which then concludes the proof that a finite product of countable sets is countable. The usual argument in set theory, I'm just going to share that with you briefly, is that essentially you can do an induction. You just have to show that the product of two countable sets is countable. And if you think about the product of two countable sets A and B, and I'm going to do that on this side of the board, to show that the product of two countable sets is countable, if you have A and B are countable, well then you can sort of write A cross B, as like, you can look at these vertical slices. These are like the lines parallel to the y-axis. If you think of the y-axis as B and the x-axis as A, it's going to be a countable union of these vertical slices. Each of these slices is going to be in bijective correspondence with B, and there's a countable number of them because they are parametrized. There's one slice for every element of A, and a countable union of countable sets is countable. That's abstract set theory. But here I love this argument because it's so concrete, it's connecting to prime numbers. I hope you love that too. And if you want more set theory, more proof-based math, check out my channel. I've got a really beautiful proof. In linear algebra, you can prove that the real numbers are infinite dimensional over the rational numbers. And you can do that using this statement. Because if the real numbers were finite dimensional over the rational numbers and it was equal to q to the k for some k, that would imply the real numbers are countable, which they're not. They're uncountable. But here you can prove, using prime numbers again, that the real numbers are infinite dimensional over the rational numbers by constructing an infinite linearly independent set of real numbers over the rational numbers. It's a beautiful linear algebra proof avoiding cardinality. Check it out. It's going to pop up on the screen over here. And if you want to refresh more set theory and refresh why the real numbers are uncountable and Cantor's diagonalization argument, check out this video over here. I'll see you in either video. I hope you love my channel. And if you're loving it, please consider liking and subscribing for lots more fun math content.